Now let's talk about logarithmic equations. Now, one thing I want you to do is to make sure you stick with all the examples I'm going to share with you in this video, as we are going to be starting with the most easiest one, and as we proceed further, we're going to be dealing with the most difficult one. So it's better you try to watch the video right from the beginning all the way to the end. Now let's begin with the first one. Whenever you have an example like this is called a logarithmic equations. When you have a pair of logarithm to be equal to some certain numbers or even equal to logarithm values. So here's what we have. Half multiplied by log of 64 to the base of x to be equals to 3. What should we do in the first case? Now, the first thing we want to do in this case is to find a way to get rid of this half. And to do that, we can multiply both sides with 2. Okay, so multiplying both sides with 2, we have 1 over 2 multiplied by log of 64 to the base of x multiplied by 2 to be indeed equals to 3 multiplied by 2. Now, to the left hand side, 2 can cancel, and to the right hand side, we can have 6. So left over, we have log of 64 to the base of x to be equals to 6. Now, what should we do at this point? Now, whenever you are left over with an expression like this or an equation like this, you can just apply the definition of logarithms at this point, which says that it's a base to which an index is raised. Okay, so applying the definition of logarithm to this point, x to the power of 6 will be indeed equals to 64. Now the next thing we want to do is to find a way to express 64 as an index of some certain value. So what should we do in this case? You notice that 2 to the power of 6 is equals to 64. So therefore, we can actually replace 64 with 2 to the power of 6. Okay, so left over we have x to the power of 6 to be indeed equals to 2 to the power of 6. Now at this point, we can apply the concept of exponential equations at this point, which says that whenever the power or the index are the same, equate the base, and whenever the base are the same, equate the power. So therefore, our final answer for the value of x in this problem is equals to 2. So x is equals to 2. So one thing I always tell my students is that for you to be sure of your answer, you can always prove it out. You can always show that your answer is correct by replacing x with 2 or whatever you have as your answer back in this expression. Okay, and just type it into your calculator, then you must result in this. If you didn't result in what is given to you as the answer, then it means your answer that you have is wrong. You get point now. So if you should replace x with 2 in this problem that we have at the left hand side, you're gonna result in 3. That's absolutely right. Okay, so now let's try to move to the next example. Hopefully you are following. Evaluate log of x squared plus 2x plus 2 to a base of 2 to be equals to 0. Okay, now at this point we can just apply the definition of logarithm straightforward. Okay, so which says that x squared plus 2x plus 2 will be indeed equals to 2 to the power of 0. This base will raise the value you are having as your answer. Okay, the base will raise whatever you're having as your answer whenever you're having an expression or an equation like this. Do you get point? That is exactly what we make use of in the previous example. So now 2 to the power of 0 is simply equals to 1. You just need to keep that in mind. Any value raised to the power of 0 is indeed equals to 1. Okay, so to the right hand side you can have to the left you have x squared plus 2x plus 2 to be indeed equals to 1 to the right hand side, as 2 to the power of 0 is equals to 1. So the next thing we want to do is to bring 1 to the side. Alright, let's subtract 1 from both sides. We have x squared plus 2x plus 2 minus 1 to be equals to 0. You know, we will have nothing left at this point. Now by the time we subtract 1 from 2, we have x squared plus 2x plus 1 as the expression we have left over. Now it turns out that the expression we are left over with is a trinomial, so definitely we can actually factorize it. So let's try to factorize it in order to solve for x. So we have x squared plus 2x plus 1. So what should we do in order to factorize this? We just need two values that when we multiply the values, it's going to give us the product of the first term and the last term. Let me use different color to make it recognizable. So we need two values that when we multiply it, it's going to give us the product of the first term and the last term. And the product of the first term and the last term in this trinomial is simply x squared. Now, at the same time, if we add these two values, it's going to give us the middle term. And the middle term we have in this trinomial is 2x. So what should we make use of in this case? Alright, it turns out that x plus x plus x can actually give us what we need. We can actually make use of them. Okay, this is not actually a factorization class. I would have shown you one of the best way you can use for you to know the two values that you are going to make use of. However, you can try to check out my playlist to look for the video that corresponds to factorization of trinomial or polynomials. Okay, good. Now we're going to make use of plus x and plus x because this will definitely give us what we want, as plus x times plus x is going to give us x squared, and plus x is going to give us 2x. So we're going to make use of plus x. Good. I need to get rid of some stuff over here. I believe we have written it. Good. So we have we just need to replace the middle term with this. That's the next thing you want to do. So we have x squared plus x plus x plus what we have 1. Okay, plus 1 to be equals to 0. Okay, now at this point we just want to group this. So let's group it. So let me use different color for you to be able to recognize it. We just want to group it in pairs, in twos. So we have sorry, that's too bad. Good. Now we just want to factorize the GCF at this point. So to the left hand side we have x to be common. Left over we have x plus 1. Okay, and to the right hand side we can say positive 1 is common, and left over we have x plus 1 to be indeed equals to 0. So we're going to be having the value of x to be equals to what? By now you should know what the value of x is. Okay, now at this point we can just equate one of these to be equals to 0 by the time we take out the GCF. So we have x plus 1 equals to 0. So x plus 1 squared will be equals to 0. Right? By the time we find the square root of both sides, okay, we just need to find the square root of both sides. Okay, so we have x plus 1 to be equals to 0. So x will be indeed equals to minus 1 by the time we take positive 1 to the side. Okay, hopefully you now get the point. And that's exactly how to solve or provide a solution to a logarithmic equations. Okay, now what about this problem? Try to pause the video and try to provide the solution to this problem. As you know that I always used to speak often, practice make perfect. Try to figure it out yourself as well, because how it tells your own ability towards the problem. You get the point? Now let's begin. We're having log of 4x plus 3 to the base of 5 minus log of x minus 1 to a base of 5 to be indeed equals to 2. Whenever you are having a problem like this, whereby you're having some pairs of logarithm expressions, okay, at one side, and you're having a single value at the other side, okay, typically you need to just observe the base of the logarithms. Are they the same? If they are actually the same, you can just find a way to apply some of the identity of logarithms to those logarithms values. As you can see, the whole expression we have at the left hand side, we can actually apply one of the identity of logarithms to this part, because the logarithms of two different values to be subtracting each other, okay, can be re-expressed as the logarithm of those values to be dividing one another. What am I saying in essence? We are trying to use the one of the identity of logarithm that says that if you have log of a certain base x such that the value turns out to be y, but another value is dividing y, let's say z, this can be re-expressed as log of a base of x to y minus log of a base of x to z. Now we are allowed to apply this concept, okay, in a vice versa way. What am I saying in essence is that if this is what you are having initially, you can turn it to this, and if this is what you are having initially, you can turn it to this. You get the point now? Good. Now this looks like what you are having initially. So we can actually turn into this. Good. Hopefully you get my point. So the first thing we want to do is just to take 1 log as the common log, since the base are the same. So we're having log of the base of 5. Okay. Then to 4x. Let me make it quite larger since they're going to be dividing each other. 4x plus 3. Then all divided by x minus 1. Then you close the bracket and you equate it to be equals to 2. Hopefully I'm communicating. Now at this point you can just apply the definition of logarithms, which says that it is a base to which an index is raised. So this 5 can just raise this 2, you know, as we have been doing it earlier. Good. So 4x plus 3 all divided by x minus 1 will be indeed equals to 5 to the power of 2. Okay, now let's try to find the value of 5 to the power of 2. That simply means 5 times 5, and 5 times 5 is simply equals to 25. So left over we have 4x plus 3 divided by x minus 1 to be equals to 25. Now at this point we can just cross multiply or multiply both sides by x minus 1. If you cross multiply, we have 4x plus 3 to be equals to 25 in a bracket of x minus 1. Okay, we're gonna have to make use of this 25 to expand the bracket because we are having 2 different values as the denominator. Good. Now the next thing we want to do is to expand what we have at the left hand side or at the right hand side to say. Okay, so we have 4x plus 3 to be equals to 25 multiplied by x and 25 multiplied by negative 1. That's exactly what we are going to do. Okay, so 25 times x is simply 25x. So we have 25x. Then minus 25 times minus 1, that's simply minus 25. Alright, at this point we just need to collect the like terms. I believe you understand what I mean by that. Okay, you just want to bring the likely terms together. Okay. Now let's try to bring any value that is associated with x to the left hand side and leave constant value to the right hand side. So definitely we have to bring 25x to this side and plus 3 to this side. Okay, good. So we have 4x and minus 25x to be equals to minus 25 and minus 3. Okay, so 4x minus 25x is simply minus 21x to be equals to minus 25 minus 3 is simply minus 22. Now at this point we can just divide both sides with minus 21x. Okay, in order to have the value of x to be standing alone, we need to eradicate whatever we have to be associated with x. Now to the left, minus 21 can cancel negative 21, and left over we have x to be indeed equals to 22 over 21, which is our final answer. Why is it equals to 22 over 21? Negative will cancel negative, and left over we can have a positive value. So that is it, guys. Hopefully you now know how to easily and mentally evaluate logarithmic expressions. If you haven't subscribed to my channel, make sure you do that now. Don't forget to give this video a thumbs up. Thanks for watching. I really appreciate it. This is the part 1 of this video. I'm gonna create a part 2 as well because we still have a lot of much more problems at which we can have a logarithmic equations. Okay, so I don't want the video to be too long. That's why I'm gonna break it into 2 pieces. Thank you. See you guys in the next video.